Hi, welcome to this new video, which is going to be very useful and interesting. We're going to learn how to draw axial force diagram, shear force diagram, and beam diagram of frames, right? We're going to start with the difference between a beam and a frame. We have a beam shown here, and then we have a frame shown here, right? So what is the basic difference here is in terms of the stress resultants, right? If you take a beam, we are going to see only what stress resultants. We are going to see only shear force and then bending moment as we represent it. However, if we take a frame, you will see additionally the presence of what the axial force as is indicated by N here, right? And then the internal stress resultants here are shown in their positive senses. This is something familiar to us already, right? On the right face, upward force, and on the left face, downward force forms a positive shear for us, and then sagging moment is positive. Additionally, if the force, axial force is tensile, we consider that as a positive force, all right? And these ones are already very familiar to us again. Okay, one can go back to our previous videos and see how these expressions are derived. And these are the positive senses for displacements that we follow here. These rules are very relevant. Okay, this will be very helpful in drawing the AFD, SFD, and BMD for frames. First rule is x-axis runs along the members axis, right? And then y-axis is located at 90° counterclockwise with respect to the axis, x-axis, right? That means if I take this member and if I say this is my x-axis, then my y-axis can't be this, okay? Because it is located 90° clockwise, right? So which one is correct then? If this is my x-axis, then y-axis should be like this, which is located at 90° counterclockwise direction. Fine. That's what this statement says. Positive stress resultants are drawn along the positive y-axis. That means, for example, if I have this force, axial force for this member tensile, then it forms a positive shear force, sorry, axial force for us. So when we draw the axial force diagram for this member, if I mark this is my y-axis and x-axis, then I'll be drawing the axial force diagram on the positive y direction, right? We'll understand it better when we go through a few examples here. And these 2 points are also relevant here. It is about the kinematics, that is displacements and rotations. These are same as what we have been following for beams. Okay. So we'll start with the first problem. We have a frame here, ABCD. The first step is to determine the reactions, support reactions, which is very simple in this case. Okay, this is a determinate frame. We don't have any horizontal force acting on this frame. Therefore, the horizontal reaction here should be 0. And then because of the symmetric loading, you should have equal vertical forces developed here, which equilibrates the external load. That is 5 kN, 5 kN, right? So that's what we do as the first step. Other than that, what is necessary here when we draw the variation of stress resultants of frames is we should fix our axis here, which will be very helpful. Okay, there are different ways in which one can do this, but this we find convenient. So this is what we are learning here. Okay, so I am marking the coordinate axis for each member here as we see. For member AC, this is my x-axis and this is y-axis. And for the member CD, this is my x-axis and then this is my y-axis. To just differentiate between this and this, I am marking x1, y1, x2, y2, which is not actually necessary. To start with, I have done this marking here. Okay, and the logic with which you mark this is start from the left joint, leftmost joint. Okay, something like this here. Start marking this here. When you go to the next joint, mark x-axis along the direction of or the axis of the particular member, then move 90° counterclockwise and mark your y-axis. Okay. For example, if I have another member here, what should I have done? I will be marking this as my x3, and then this or this as my y3. This as my y3. Okay, because this is my counterclockwise direction, right? So that's what I mean here. So we already have determined the reactions. We are going to do what next? We are going to draw the free body diagram for each member here. Okay, now to do that, first we need to take this member. We are going to make a surgical cut of the member AC somewhere here. Okay, and we are going to show it here. We need to also consider this reaction here, right? So this reaction is shown here, and we made the cut here. Okay. Similarly, we are making a cut very close to the joint here, and we are also detaching the joint. The joint is shown here separately. Okay. So first we start with the member AC. We already have the reactions here. Now we go to the right end. Okay. So this element AC should be in equilibrium. Similarly, each of the elements, including the joint, should be in equilibrium. Only then when we combine all them, put together all of them, the entire frame remains in equilibrium, right? So that's the logic. Therefore, if we come to the right end, we should have internal stress resultants which keep this portion in equilibrium, right? So you don't have any axial force here. That means the axial force here should be 0. And if you consider moment equilibrium about this point, you will see that 10 into, if it is A, 10 into A is equal to 5 into 2A. This already satisfies the moment equilibrium. Therefore, you don't have any bending moment coming here, right? And then finally, what should be the value of shear force here? It has to be upward 5 kilonewton. Only then this plus this will equilibrate the external load applied here, right? So once you determine all of them, you need to show the same values here, but in the opposite sense, right? If it is upward, this should be downward. If it is rightward, this should be leftward. I mean the horizontal forces. And finally, the bending moments, if we consider if this is counterclockwise, this should be clockwise. Even though these are often just to clearly explain these aspects, I have shown this here, right? So if we consider the equilibrium of this joint here, you need to show again this pass in the opposite sense here, so that if you consider equilibrium, it is trivially satisfied for this joint. However, if you have any external load or bending moment applied here, we need to be a little more careful. We'll see that in the subsequent video. Fine. Finally, after marking the values here, we are coming to the next element, CD. Okay. Here we already have this reaction shown, 5 kilonewton. Now we need to take this pass at triads. Okay. Show them as we see here in the opposite sense, so that if you join these two, they will be in equilibrium, right? And after doing that, you can check whether this element is independently in equilibrium or not. You can see that this is in equilibrium, right? Because just you have only the axial force. This is 5 kilonewton upward, this is 5 kilonewton acting downward. So this is a compressive force acting on this element CD. Other than that, you don't have any shear force or bending moment acting here. So after drawing the free body diagrams, the next step is to construct the SFD BMD and AFD of each element. We are just going to take the element AC first of all. Okay. So this portion I am taking, this free body diagram I am taking as such, and I am drawing it here. Then whatever axis I earlier decided, I am fixing it here. Okay. This should not cause any problem as such, because we are already very familiar with drawing the SFD and BMD of beams, right? So same goes here, same logic goes here, because usually we consider x-axis like this and y-axis like this for our beam. So this should be straightforward, right? Just the extra thing what we consider here is extra diagram. What we have here is the axial force diagram. Or you see that this element did not have any axial force acting on it. So this remains flat with a zero value, right? So this is just simple. Next, if we consider the element CD, I need to take this free body diagram. Okay, I am drawing it on this page, what we see here, right? And then I'm marking the axis like this, y2, x2, whatever I fixed earlier. Now again, we see that you don't have any shear force and bending moment acting on this particular element CD. Therefore, shear force diagram is 0, remains 0. I mean, this also remains 0. Bending diagram is 0. However, if you consider the axial force, you have a constant value of axial force acting throughout this element CD. But for us, if you have an axial force which is tensile, it is positive for us. But we see that this is a compressive axial force, which is pointed toward each other, right? Therefore, this should be a negative one. How do we draw it for this element CD is, if this is your positive y-axis, we need to draw it just in the negative y direction, because this is a negative axial force. Okay, that's why we drew it here instead of drawing it here. All right, that's all. So you have these three variations for each of those elements. Just combine them together to get these variations that we see. Right? Looks beautiful. We'll go to the next problem. Okay, but you see that I have the same variations shown here. What's happening here? I didn't make any major difference here. What I did is, in the earlier problem, I had a pin support here and a roller support here. Just in this problem, I swapped them. do they cause any change? I mean, the interchanging of supports, will it cause any difference in the AFD, SFD, and BMD? As I told earlier, I drew it as such, so they remain identical. Okay, what difference is there then between the first problem and second problem? If you draw the reflected profile, however, it will be different. Okay, so you can try this problem and see how it works. Finally, we'll go to the third problem. We have again a simple frame shown here, a lateral load acting here, right? First step is to draw the support reactions, to determine the support reactions, sorry. So you have this horizontal force here, therefore there will be a horizontal reactive component as well here. Okay, so you can directly do it, find the reactions, then mark your coordinate axis. So we start with element AB. I'm marking along the axis of the member X, counterclockwise 90-degree Y. Then I come to the next element BC, I'm marking it along the axis of this element BC, again counterclockwise 90-degree Y. Okay, that's all. Let's draw the free body diagram. Once you're familiar with the free body diagram, drawing the free body diagram, you don't require the joint as well. Okay, yeah, see, you can see that I didn't show the joint here, right? So we'll start with the element AB first of all. You need to draw this reactive components here, or I mean, represent the reactive components here along with the external load. Okay, be mindful about all these aspects. Now, when you come to the top joint or the top end of the column, you need to see what are these three values required to keep this portion of, this column in equilibrium, right? So you see that sum of horizontal forces is already satisfied here. This equilibrates this. Therefore, you don't have any shear force existing here for this element AB. However, you see that now to equilibrate this 6 kilonewton force, this 6 kilonewton is required here, which is the axial force for this column. And finally, if you consider moment equilibrium, this 12 into 3 forms a clockwise moment, right? So you should have 12 into 3 counterclockwise moment as well to ensure moment equilibrium for this element AB. Okay, so that's how we finish this ones. Now, when we move to this neighborhood, the next element, just to put all these values here in the opposite sense, right? So this is rightward, hence this is leftward, this is upward, this should be downward, this is counterclockwise, this should be clockwise with the same magnitudes. That's all. You already have the reaction here, right? So directly you take the first element and draw the AFD, SFD, and BMD. So we'll start with the AFD. This is 6 kilonewton force, which is a tensile force. So we should be considering it as a positive force. And mind that this is our y-axis, right? As this is a positive force, we need to draw it along the positive y direction. That's what we have done here, and we marked it plus. This value is 6 kilonewton, right? Then SFD BMD is similar to what we usually do, just that you need to be cautious about the sign convention. That's it. Okay. So if you consider this as our beam with our y-axis like this, you can see that the positive shear is like this for us, right? And then positive bending moment is like this. So just we need to be mindful about that. Then we can finish the SFD and BMD. So we see that the shears, what we witness here, are just opposite to the positive sign convention what we follow. That is, if you consider this as the right end, the shear force should be acting upwards to be considered to be positive, but this is acting downwards. Similarly, if you consider the left end, this is acting upwards, which is also negative. So therefore, we need to draw the shear force diagram on the negative y direction, right? So see, this is our positive axis. Therefore, we are drawing it in the negative direction, negative, and the value is 12 kilonewton, right? Finally, the bending moment diagram. I just repeated the shear force diagram because we usually uh, combine them and see the variation. Okay, so it helps always. The same manner, I can say here that we have the relation dm by dx equal to minus v, which means m is equal to minus integral v dx, right? So when you find the area under this diagram, you should get the bending moment diagram, and we need to have a negative sign considered. So 12 into 3, okay, with a negative sign. Already this is a negative area. Negative of negative will be positive 36 kilonewton, right? And then you don't have any moment here, so it should start with a 0 here, bending moment diagram. And then you can cut a section right 12 times x, we'll see that it varies linearly, and when it reaches the other end, it should be equal to the moment acting here, which is 36 kN. And mind that this is a positive moment, because for us, this will be our positive bending moments, right? If this is our y-axis and this is our x-axis. It goes as what we did for beams, all right? And if we consider the other element BC, we have drawn the free body diagram here, okay? We are taking this and drawing it over there. And axial force, we don't have any axial force acting on this in this beam BC, therefore the axial force diagram is 0 straight away. And what about the shear force diagram? Right side upward, left face downward, so this is a positive shear, so we need to draw in the positive y direction plus 6 kN. Done. Then how about the minimum diagram? Minimum diagram should be again, see, you can see that this is our left hand. So in our left hand, see, this is our positive sign convention for bending moments, right? So this is acting in the positive sense. Therefore, we need to start with a positive value here, all right? And then it should reduce until it becomes 0 at the right hand, because we don't have any bending moment acting here, all right? That's all. This completes the construction of this internal stress resultants for each element. Join them together, combine them, you get the axial force diagram, shear force diagram, and minimum diagram. All right, that's it. Thank you so much. We'll meet in the next video again.